Feel uninvited. Left home in West LA, I'm not excited. So uninspired. On my way to play the bay while you're alone. This girl's a wonder. She loves me, yeah, she needs to know I love her. I wonder if we'll make it through this summer. Just wanna touch like back when we were younger. Yeah. Why don't you love me, love me, love me? Touch me, touch me, touch me no more. Why don't you love me, love me, love me? Touch me, touch me, touch me no more. Love me, love me, love me. Touch me, touch me, touch me. Love me, love me, love me. Touch me, touch me, touch me. I'm so divided, starstruck, but hate has got some indecisive. I'm over fighting. I just can't wake up cold and sleep alone. This boy's some trouble. When he's around, my problems seem like double. His stupid eyes put me on ice, so no, no. Don't slow me down, don't wanna do this solo. Why don't you love me, love me, love me? Touch me, touch me, touch me no more. Why don't you love me, love me, love me? Touch me, touch me, touch me no more. Love me, love me, love me. Touch me, touch me, touch me. Love me, love me, love me. Touch me, touch me, touch me. I can't help myself, you're attracted.
Hello everyone, I am back for more hacking practice. On today's stream we will be doing more of the angr CTF that's sort of designed around teaching the features of angr and giving room to practice it. This is something that we started on last week, probably Friday, I guess. And so we're going to continue with that, and if everything goes well, we will move on to trying to use angr to solve the next set of challenges in the Nightmare CTF. So just to give that context again, we have 6 challenges in the sort of symbolic execution type of challenge category. And before I dive into those, I want to finish up with the entries in this angr CTF thing. So we've gone through 7, and so we'll start on 8 and see how far we can get through this. So I'm going to copy in .08 and the scaffold file, and let's look at the scaffold file. Okay. So check equals, it's not doing a string compare call. It is manually checking it, which seems fine. What is the name of this one? Angr constraints. Okay. Well, you as a human can easily determine that this function is equivalent to simply comparing the strings. The computer cannot. Instead, the computer would need to branch every time the if statement in the loop was called 16 times, resulting in 2 to the 16 or 65,000 branches, which will take too long of a time to evaluate for our needs. We do not know how the complex function works, but we want to find an input that, when modified by complex function, will produce the string. In this puzzle, your goal will be to stop the program before this function is called and manually constrain the toCheck variable to be equal to the password you identify by decompiling the binary. Since you, as a human, know that if the strings are equal, the program will print good job, you can be assured that if the program can solve for an input that makes them equal, the input will be the correct password. Okay, so I believe what they are saying effectively is we need to use angr's capabilities of like tracking all of the relationships between the 16 bytes that are in input, or 128 bits that are in the input variable, all the way through, and connecting them mathematically through whatever, or logically through the set of instructions inside of complex function, so that it knows the connection between encrypted inputs 128 bits and the original inputs 128 bits. The problem then is the behavior of continuing that process, tracking now the single bit effectively. Technically it's like going to be 32 bits coming out of check equals, but we know only one of those bits will be set, as presumably, because of the equals equals comparison. So angr could, or I guess generally would, attempt to continue its process of tracking all of the mathematical relationships and allow us to find the connection between input and the one bit that comes out of check equals. The problem is the way that check equals works is so branchy, I guess is one way to put it. It has so many different possible outcomes, because even though the end result is a 0 or a 1, we would get zeros in... Oh, I see. So part of it is like it doesn't quit out early, right? It's gonna... This is like a... if you attempted to write a time, constant time string compare, constant time in the sense that like it will always take exactly the same amount of time for the same input length, rather than be shorter if the first bytes aren't equal, for example, which I believe the normal string compare would do. So when you're trying to eliminate timing side channel stuff, you might use an approach like this, which makes sure to go all through the entire input before deciding what the result is. And part of the outcome of going with this kind of algorithm is that num correct could be anywhere from 0 to 16, but the ways in which it can get from 0 to 16 ultimately have 65,000 possible routes to get there, I guess. So that becomes a really large number of potential states for angr to check. And what they want us to do to practice avoiding that difficulty with angr is basically we'll put our constraint that encrypted input needs to be exactly equal to whatever the string is that it's actually comparing against. and then we will not care at all about doing this function, simulating it with angr. Because if we can like know ahead of time how to constrain what encrypted input has to be, we don't actually need to have it run dynamically the comparison function, since we can verify by doing some binary analysis, some reversing on it. Let's see. So it is a different function here, but if we look inside of that function, you know, we can double check. Okay, gets that, and it adds the same number with the password static variable, I guess is where it stores it. And then if they are equal, then we add one to the number that's tracked. So, I mean, it has this behavior. Just looking at the binary, looking at the assembly here, it does what the script comment says. So, since we know that the overall impact of running that function is just going to be yes or no, whether this string, the encrypted input, so our buffer object is equal to whatever is in obj.password, then we just want to set that constraint, I guess. Okay, cool. So our start address, I mean, they could have us do a start address that is, I guess we'll follow what they suggest. And they're presumably telling us to start after scanf because that's how they've done all the rest of these. So we will start at this address, and it is helpful that we are using a statically allocated buffer. So I think password is going to be obj.buffer. Or rather, okay. So we'll use that memory address for our symbol. And, oh, sorry, the length is going to be 128 bits, and the address is that. So we're going to store our symbol into the memory for our state. And then we need to put the address to check constraint. So I guess just before the call, or just generally when we get into this block is fine, because we'll get there after we've done all the modifications. So we want to find that constraint, or rather we want to find that address, and then constrained parameter address is going to be obj.password, was it? Yep. Which is weird. is it not? It's empty. That's interesting. Where does password get filled in? Oh, I guess right here. Okay. But that's fine. It'll get filled in for us by the program. We don't have to know what it is. And then in bytes, it's going to be 16 bytes. So then we're going to load that now. Yeah, okay. I don't know why load takes a number of bytes rather than a number of bits, but I guess, you know, it's fine. You're not going to try to load less than a bit. At the same time, you could potentially store an odd, like a non-multiple of 8 number of bits, because you don't give the length when you do memory.store. You just give the bit vector that you want to store, and the bit vector can be any number of bits. You could put 7 bits if you want, or 37 bits, doesn't really matter. We want to constrain the system to find an input that will make constrained parameter bit vector equal the desired value. Wait, what? Maybe I am... Right, so we're loading... Oh, this is loading the address that is passed in. Okay, so that's this one. I'm definitely confused now about what... Oh, sorry, not the start address, geez. What password address is about. Like, if password address is not... I guess we'll put the... Maybe you could do it either way. And it wouldn't necessarily matter. But... Well, we'll give it a shot. So, password address, we're like creating a bit vector symbol that's the 16 bytes long, and we're giving it the address of obj.password, which is where the program is going to store. Yeah, like I don't... So if we store the bit vector in memory, but start the program down here, it's not going to run the code that stores the actual string, the thing that needs to be compared against. So I have no idea what this is for. And in fact, it doesn't seem like it's being mentioned anywhere else. Yeah. I'm gonna delete this because I don't understand why it's in there. I don't think it is useful for us. So, so for desired value, we can, I guess, just put in a string and it'll convert it for us. So we have 41, 55, 50, 45, or 44 rather. Yeah. Okay, so it's just the name of that function. AUPDNNPROEZRJWKB. So that's the value that we want to use, and then we're going to set up a constraint expression, which again doesn't get mentioned anywhere else. So why don't we, can we, oh, I see, we probably can't, I don't know, we probably can. Because this equals is going to be overloaded to return not true or false, but an actual constraint, would be my guess. In which case the bit vector has to be on the left-hand side of this comparison, because string is not going to overload equals in the way that we need it to. And solve for the constrained parameter bit vector. So constrained parameter bit vector, solution state solver.eval cast, I think cast2 equals bytes. I guess we can see if that works. I don't feel great about like, oh, I deleted some stuff from this script, but I mean, what we have right now makes sense to me. We'll start after the scanf. We will run until we get to the beginning of this block, meaning we've done all the modifications using complex function. And then, so that's the address that we are looking to find. When we find that address, the explore process stops, and what we will do is add a constraint that the bit of memory at obj.buffer, wherever that is, this address here. Why is this a different address? That's weird. I don't know what I copied incorrectly. But the value at that address needs to match this string, is the constraint that we're putting on there. What was the value that I had before? 85B3. Somehow I got the beginning of the main function address. Okay. Alright, let's find out if I messed stuff up. Could not find the solution. Okay. So we didn't hit this address. It's interesting. 48669. Why wouldn't we have hit that address? Well, why don't we start the entry state? Okay. But that's the wrong thing to print, I guess. Not right. We need oh, that's I guess what password was for. Okay. So like this. And probably typed it wrong. Well, didn't crash immediately. But it also didn't get anything from that bit vector that we stored. So, oh. Okay, so we need to maybe I'm just thinking about this wrong, but can we go after memset? I don't know. If we put a bit vector symbol at the address that we read into with scanf, and then that value is modified before it is checked. When we solve for that bit vector, is it it's all zeros because that's what the initial value was. So we do need to start after scanf. Or, I mean, what we could do can we run to the address after scanf? And then throw, or what is it? Raise in Python. Didn't get to after scanf for some reason. Otherwise, what is the, we need to move it back into the active. And I don't remember what the simulation manager, stashes, how do we move stuff between stashes? Move. I guess we'll just move everything. Just move, okay. And then we want to say state dot memory dot load (16 bytes). Okay. Right, and then that's what we will solve for. So the bit vector that we get by loading the memory after scanf has done its thing. Yeah. All right, cool. So I'm not sure what was preventing it from working when we just started after scanf. We could certainly try it again. So we could say start at that address. What's a blank state? Put I guess we need to load it from memory. And then move. That one doesn't matter. Let's see if this works. Yeah, it doesn't get to where it needs to go if we just start after scanf. For some reason, so you're setting local ch0. Local ch is based on EBP, so maybe the issue is we need to set set it to ESP. We can set it to ESP plus 14 hex. Still didn't work. And why did it not show like it was running at all this time? Yeah, I guess it's because I fixed the EBP references, so we're just not getting those warnings. But let's see. So we throw 0 in there. We put 15, the EAX. EDX is that, EAX is, yeah. Just trying to see if we are referencing anything. That hasn't been set, but it really seems fine. Maybe part of the issue is that ESP is now maybe less than it was. So let's see. Do we, I mean, other than, yeah, we don't actually need anything else. So it's very confusing to me that we're not getting to here. When we try to set up the stack properly. Try that. See if that helps at all. No, I don't know why starting after scanf at this point doesn't do anything. Doesn't work properly. Yeah, what could be causing that? I guess let's look at see what the stashes are. ducks. Not gonna go to where we want. Okay. Just dot stashes. See what it looks like when it fails. We've got one in dead ended, which is at 81303D0. I don't know if that's the memory address in Python. I think it's the... So how would we get to there? What does that mean? Are we... doing something unusual? Whatever, I'm not going to worry about it. I don't think that I'm going to ideally take the route of just start in the middle of the code unless I really have to. So the fact that that didn't work on this one, and I don't understand why, that's frustrating to not understand why it wouldn't work in that approach. But I guess it's not critical to understand. So let's move on to the next one. Okay, so this is hook. So level performance of following computations, get 16 bytes of user input and encrypt it. Save the result of check equals similar function to what we had in the one that we just did. Get another 16 bytes from the user and encrypt it. Check that it's equal to a predefined password. Okay. So I'm not sure that I understand fully their explanation. So we're setting up the check results. Scan in password. Like all of this is the exact same as what we just did. So scan in a thing and then get whatever true or false value from checking if it's equal to this string. Put that in obj.equals. Do we do anything with obj.equals? Yeah. So then if no, because we just overwrite it right there. I guess we check it here. Yeah, okay. So we get that result, then we run it again. We run complex function on the password value we stored up here. And if the password value is then equal to, or the modified password value, encrypted I guess they call it, is equal to the second string that we input, No, we just read it in. We don't. Okay, and then we compare. Yeah. If it is equal, okay. So but I think the key here is that get another 16 bytes from the user and encrypt it is not correct. We get 16 bytes from the user, but we are comparing it against the predefined password, but encrypted. So first we need an input that encrypts to this value. And then we need an input that this value encrypts to, which is fine because, I mean, we could calculate that manually if we wanted to, really. Okay. Yeah, so, I mean, but the point of this one is to skip the behavior of this call and not have angr try to run it as part of its simulation. So the address of check equals where it is called, actually. Okay. Can I actually see that? Yeah. Okay. I'm lucky enough that it's in this part of the thing, but something has happened with my radar config, and I don't know how to get the. I don't know how to get this view to show me addresses for each instruction. I feel like I used to be able to do that, but whatever the key combination was, doesn't work anymore. Is that the right address? Yeah, B3. Okay. So that's where we call it, and then the length parameter in angr.hook specifies how many bytes the execution engine should skip after completing the hook. This will allow hooks to replace certain instructions or groups of instructions, determine the instructions involved in calling check equals. So we probably also want to skip the modification. No. So maybe we need to skip from why are we subtracting 8 from ESP and then pushing stuff? Oh, I see. That's fine. So, right, because this will make a total of 16, which we then add. So we want to do this instruction, I guess. And just because that'll clean up the stack. So, okay, let's go ahead and see what that length is. So it's B8, so that's a 5-byte call. Okay, skip check equals. So input buffer address is going to be obj.buffer be this address. Oops. Okay, I don't like that view. And then the length is 16 bytes. So we'll load that from memory. The string we want to check against is going to be X, Y, M, K, B, K, U, H, N, I, Q, Y, N, Q, X, E. And let's see. Determine the address where the user input is stored is passed as a parameter of the check equals function. Then load the string. Okay. Reminder, the state.memory.load will read the stored value at the address, user input buffer address of byte length, user input buffer length. It will return a bit vector holding the value. This value can be symbolic or concrete depending on what was stored there in the program. Sure. Determine the string. This function is checking the user input against. It's in the name of the function. Yeah. GCC uses EAX to store the return value. If it is an integer, we need to set EAX. I see. Okay. However, since we are describing an equation to be used by Z3, not to be evaluated immediately, we cannot use Python if-else syntax. So we can't just do the comparison and say EAX equals 1 or EAX equals 0. Based on that, we need to give a, what do they call it? Operation or an AST node, basically. So these are nodes in an AST, and the if is its own kind of node with this constraint being the value that will determine whether it evaluates to this one or that one, and Z3 will use it to do the sort of solving that it needs to do. So that makes sense. But yeah, we can't just write it as normal Python. Okay. And our success case is if we print out good job. For failure cases, print out try again. And then we do the standard stuff. Yeah, so then we need solution state POSIX.dumps sys.standardin.file number. We'll print that. So what we could do is say print both of them because there's two entries. All right. So let's see. Those are correct. Yeah. Cool. That makes sense. The hooks is what I thought we were going to do the last time, but I guess there's a way to also just say, if the details of your scenario work out that way, then you maybe don't have to go past this function. You could just skip it, but hooking it makes a lot of sense to me as an approach to use. All right, we'll move on to number 10. And there's a total of, was it 17? Yeah, but we're making okay progress, I'd say. Maybe we'll get through all these today. This one is similar to the last one. I don't know what it is. What's the name of it? Sim procedures. I see. This one, I'm trying to remember from the docs. A sim procedure is kind of like a hook. And I think you just register it as the address. It's more like hooking the address of the function. So if the function gets called several times and you always want to replace it with some particular Python implementation, yeah. It operates under the same premise that you will have to replace the check equals function. In this case, however, check equals is called so many times that it wouldn't make sense to hook where each one was called. Yeah. Instead, use a sim procedure to write your own check equals implementation and then hook the check equals symbol to replace all calls to scanf with a call to your sim procedure. All calls to scanf. Wonder if that's just a typo. Why can't I just use hook? The function is called many times, but if I hook the address of the function itself rather than the addresses where it is called, I can replace its behavior everywhere. Furthermore, I can get the parameters by reading them off the stack with memory.load, regs.esp, dus plus xx, and return a value by simply setting eax. Since I know the length of the function in bytes, I can return from the hook just before the ret instruction is called, which will allow the program to jump back to where it was before it called my hook. If you thought that, then congratulations, you just invented the idea of simple procedures. So yeah, if you wanted to actually hook the function itself rather than the call sites for all the functions, then, well, they've already implemented that behavior for you. And it's called sim procedures. Instead of doing all that by hand, you can let the already implemented sim procedures do the boring work for you, so you can just focus on writing a replacement function in a Pythonic way. As a bonus, sim procedures allow you to specify custom calling conventions, but unfortunately is not covered in the CTF. Okay. So we do the entry state, define a class that inherits angr.simProcedure in order to take advantage of angr's sim procedures. Okay, so we have to subclass it in order to implement that. A sim procedure replaces a function in the binary with a simulated one written in Python. Other than it being written in Python, the function acts largely the same way as any function written in C. Any parameter after self will be treated as a parameter to the function you are replacing. The parameters will be bit vectors. Additionally, the Python can return in the usual Pythonic way. Angr will treat this in the same way it would treat a native function in the binary returning. An example, add if positive, int a and int b. If both of them are greater than or equal to 0, return a plus b, else return 0. And our replacement says def run has self ab. If a greater than or equal to 0 and b greater than or equal to 0, return a plus b, else return 0. Cool, cool. This is probably as close as you could get to having a nice DSL for this in Python. Or I say probably, I'd say it is as good as you can get in Python, which isn't terribly well suited to doing this kind of DSL. But you know, they're overloading all the stuff to get the proper results out. So sounds good to me. Finish the parameters to check equals function and reminder. That's the so we want to match this signature. We can almost copy and paste the solution from the previous challenge. Don't look up the address, it's passed as a parameter. Okay. So can we just say to check? Probably not, right? Well, no, because that is the value that is passed in. It's a pointer to check. So okay. Then we load the value from that address, specifically 16 bytes. we want to check against a certain string. So we got to find out what that string is. Sorry. And it is this. Okay. So then if user input string is equal to check against string, then we want how do I do it? Can I just say clarify.bvv 032? I guess it's probably 1 if they're equal. JKUE, hello, welcome to the stream. Urjukwe, I don't know. What language is hacking use? Well, over here we've got Python. And then on this side, we're using Radar to do reverse engineering or disassembly in particular. So, I mean, this is not a specific language, but, you know, if we look at this, then this is assembly code. What language does hacking use? I mean, it can use lots of different languages. So right now I'm finding value in knowing assembly language because I'm doing this sort of low-level binary analysis work. And I'm also finding a lot of use in Python on this side because I'm using a program or a particular like technology that is implemented in Python, and the way that you make use of that particular technology called angr is you write Python code to run it basically. So it's like a Python library. You need like kind of a IDE to do that because I know Python. I'm not sure what that is in your sentence. I do most of my Python coding in Vim or Emacs because those are what I'm comfortable with. But obviously you can do it in any kind of IDE thing. Atom, VS Code, whatever the Python one is from the people that make Sea Lion, and a bunch of other IDEs. I forget the name right now. They started off as a Java thing, but you can definitely, you use a lot of different programs to write Python. The disassembly stuff, I wouldn't call it an IDE, but you do need like a disassembler program, which is there's only a small handful of them that are sort of well implemented. There's like IDA, Binary Ninja, Ghidra, and Radar are probably the big four. And there's a lot of complicated stuff involved in doing a disassembler, so you really do need a particular program for that. I'm not sure which thing you're referring to by IDE. Do you mean this thing on the right hand side, where I've got the mouse right now? I will get back to what I'm doing, but let me know if you mean the thing. Yeah, how does it work? I mean, I know Python, but how to case to heck? I mean, there's a lot of steps, But if you know Python, you can look at the information for this angr tool, which is what I'm using. On the right-hand side. Okay, so on the left-hand side, I'm using a library called angr. There's the documentation, where you can just go to angr.io for the main page. It'll give you like an overview and stuff. And then on the right-hand side, I'm using radar for doing disassembly work. Technically, it's called radar 2, I guess, but they also have a GUI version. I'm just like SSH'd into a virtual machine, so I'm not using a GUI for any of this, but you can definitely use Cutter, which, you know, is probably a nicer experience, let's say. And it'll give you the same results. It's it's just a user interface on top of the same radar program, so you can see all of this. And apparently it actually implements the decompiler from Ghidra, so you can even get back to relatively nice C code. I say relatively because it's never going to be quite as nice as the original, but I guess if you do a lot of work and you have put in the types for everything, then you can definitely get code that looks like this, apparently, so that's nice. What are you doing? I mean, what will the program do or hack? So right now I'm just doing practice with this angr tool. So they've created a repo of a bunch of small programs to hack, and just as a way to like help you learn. So let me do one of the ones that I've already figured out. So if I run this program, it wants me to type in some kind of password, and it's going to fail if I type in the wrong password. And if I look at it in radar, so if I disassemble it and then go into the code, we see it takes my input with the scanf function and then does some stuff, and eventually it calls this complex function, which is like a kind of like an encryption algorithm, and I think it ends up calling this once on every letter in the program, or sorry, in the input that I gave. So I could spend a lot of time and try to reverse engineer this. It's actually not very small. It's not a very large complex function, let's say. I think this is sort of a stand-in in the case of these example programs, but real world ones might be 10 times as long and just full of all these like move, shuffle, or shift rather, multiply stuff. So it would be kind of annoying to manually reverse engineer that. So instead, you can write a script which, I'm not in the VN for there. Okay, I can run it on this side. I can run this script and it will use the angr program to sort of simulate running the binary. Maybe that was a poor example choice. Oops. 06. So they all work the same way in this sequence. They all say enter the password. I can type whatever in and it doesn't work. But if I if I run the Python script that uses the angr program, or this is the command I ran actually, then it's basically attempting to simulate the program, and with the right like configuration and instructions to angr, I can say, hey, simulate it until you can tell me the input that ends up causing this program to print good job, which is the success case. So now if I run it and I paste in that input, it prints out good job. but I would have had to manually go and do a lot of work to figure out how to get back to this exact input if I were doing it entirely manually with Radar. So that's all that I'm doing right now. It's not, particularly fancy hacking of anything, but it's sort of, it would be used to hack things that are more complicated, I guess. I mean, mostly CTF challenges is what I'm interested in. But yeah, hopefully that has been somewhat informative. I don't know. I think maybe calling it hacking is going, in my mind, it's a aspect of hacking, and it's part of my series of videos that I'm doing about practicing hacking skills related to binary analysis and exploitation and stuff. But this is definitely on the low end of exciting stuff compared with a lot of hacking activities you could do, let's say. Thanks for the follow, by the way. So need to finish filling out the stuff in this script. Okay, so we want to hook the check equals function that is in here, which is at this address. So throw that in, and then our success case is if it prints good job. And our failure case is if it prints try again. And then the solution that we're looking for is going to be solution state.solver dot that's a good question. What do we want the solution state to be? I'm guessing we want it to be whatever was scanned into here. Or, oh, it's a stack variable. So, oh no, we just want the input. Solution state dot posix dot dumps sys dot standard in dot file number, and decode that. See if that goes. All right, so it says that is the right input to give. So if we check it, prints good job. Excellent. So again, like in terms of the actual result of what I am doing, none of these are going to be very impressive or meaningful results. It's more, each one of these is showing me a different technique for how I can use the angr program to do a particular thing. So this one was showing me how to replace Radar really doesn't like these giant functions. Can I just tab? Here. At some point, I would think, oh boy. Oh, well, I mean, I don't actually need to see it that way. So I'm just telling angr, when you're simulating the program, don't actually simulate running the code for this. I have replaced the code with some Python that does the equivalent. So go ahead and just run my Python and don't run this thing because it's very complicated to simulate this thing. So that's the technique that they're showing off. which is definitely handy if you've got weird, complicated functions that you know that you don't need to actually simulate. You can just replace them with Python and it'll do the right thing for you. Okay, and it sounds like we're going to do the same thing for scanf in this next one, just based on the name, sim scanf. This time the solution involves simply replacing scanf with our own version, since angr does not support requesting multiple parameters with scanf. The thing is, this is like 3 years old, so it actually does support multiple parameters with scanf at this point, but might as well give it a shot and see how that works. Yeah, do I do args on this one? What do I want to do? Oh, you know what? What I can do is I don't need a full scanf simulation. I can look at how it is used. Ooh, maybe I can look at it. It seems to be a very large program if it's taking this long to render the graph, or a very large function. But we can see where scanf gets used, possibly. Is it doing the same nonsense? Ugh. Friggin' rather annoying. Okay, bunch of scanf calls, but they are. Why is it doing? I mean, if it does a bunch of scanf calls, like, do we need to send a whole bunch of input? Because wouldn't you want it to be scanf if it weren't actually reading from standard in? Maybe they redirect standard in for something. I don't know. But we know that there's 2 parameters, so we actually don't need args. You can do scanf1 address, and then the size of this is going to be 32 bits because it's 2 unsigned integer parameters. Okay. And we want to store our bit vector symbols into memory at the addresses that were passed into scanf, using the endianness of whatever the system is. Now we want to set aside references for our symbolic values in the globals plugin included by default with the state. You will need to store multiple bit vectors. You can either use a list tuple or multiple keys to reference the different bit vectors. Okay, so I think we want scanf 0 and scanf1 here. And then scanf itself, I guess we will override the import. Okay. So we'll switch that. So solution is going to be do? Solution state dot solver dot eval stored solutions, or just s for s in. You know what? Let's just do. Do we, maybe I am, why do they call it stored solutions down here? Is that implying that there's got to be multiple ones? Guess we'll find out. Yeah, let's see how that works. I don't have a lot of hope. What did I do wrong here? Interesting. Is that really? Nope, that was not it. Still don't think, yeah. VWXS, XS, X, SXFW? No, okay. So, what am I doing wrong here? You'll need to store multiple bit vectors. Okay, so how do I want to do it? Nil or none. That's what it is in Python. Then I see. How do I want to go for it? Just do it this way. Okay, and then so let's see what that looks like. It's not going to give me output in the way that I need it to. Int is not iterable. Why can't I do it that way? I'm probably just too... I've been coding in Clojure all day and all last weekend, so... Oops, didn't mean to run it again. It's not going to work still. Okay, so... Okay. Nothing in solution 0. Is that not right? Going to be very spammy, I imagine. No. Oh. I see. What is the... something like that. Okay, so it still only found one thing. That's interesting. Maybe the solution is to put them in the other order? Oh, but they need to be numbers. So I don't want the actual solutions. What do I need these for? Why do I need to evaluate these? Can't I print out standard in? It's gonna be right. I need it to as integer. I've just made this more complicated than it needs to be for sure. Okay, let's see if I put this one. Yeah, okay, so it was the right thing. I was just printing it as bytes, which by coincidence, well, probably not coincidence, but it happens that the numbers in this case were also a sequence of uppercase letters, which is what all of the text-based passwords have been so far. And then in failing to recognize that, because I don't know why, but they were doing %u in the scanf, so of course I needed it not as strings. But I made the program more complicated than it needs to be for sure. Oops. Why don't we just say okay, so is this printed out in the appropriate way? Yeah, cool. All right, that's all that I need for that one. Vera testing. I've heard about this in the docs that I was reading, but I don't know anything about it. They were a little bit coy about it. What? This one is empty. Cool. Okay. Let me just browse through the remainder of these scaffolds, see if there's stuff meaningful. Okay. So if you have a static binary, you can find where we're calling the actual library function through whatever means are available to you. Maybe your disassembler is good enough to figure that out. If not, maybe you can figure it out manually. In that case, you can then do some sim procedure hooking replacement stuff. What is 14? Shared library, arbitrary read, arbitrary write, arbitrary jump. This one looks like it's maybe a little closer to doable. Okay, because I don't know what I should be doing What do we have with 12? Fair testing, yeah. Like, I guess I can apply that alt thing. And we say var testing equals true when we make this angr. It did figure it out. Okay, nice. Self model get any node. Okay. I don't know if that was in our code. No. Yeah. So the thing about history line merging, my recollection is that the veritesting thing or certain execution approaches are designed around the concept of you could go down a bunch of different paths and have a bunch of different state objects from all those paths, and when some of them join back up, and you know it doesn't matter what had happened before, if they all get to this point in the program, if they get to this address or something, then that means they're basically effectively the same state. Then you can merge them back together, minimize the amount of simulation you have to do. So I'm assuming the veritesting program is designed around that concept. Yeah, I don't know. Let's see what the difference is here. So we have our input that is 32 characters long, and we have 3 stack variables that we initialize to 0, or well, 38. Yeah. 38 is the loop per character on our input. We go in, we do complex function, compare EBX and EAX. What is EBX from? It is the byte. So if the result of complex function is not equal to what the original was, I guess, then what is the 4b that we're pushing to complex function? I'm not sure. So if they're not equal, then we add 1 to 38 and keep it going. If they are equal, then we also add 1 to 3c, and okay, so when we get down here, if 3c is 32, so that's weird, right? Oh, I see. It'll also just go to try again. But if they, so if complex function is the same, that like if the output is the same as the input, is that accurate? What is it we are going to compare against? I guess we aren't comparing against anything. That's the tricky business. Okay. So if they are equal, then local C, if it's not 0, or sorry, if it is 0, then where do we set local C? What is 34 used for? Weird. So 2D is our input buffer. C is something from the thread storage, maybe? Okay. Let's see. Does that get changed in GF? Doesn't look like it. But yeah, so I'm not 100% certain, but I guess the general design in this one is you need to give an input that for every character the complex function ends up returning the same thing, ends up being kind of the identity function, a very complicated identity function. And so maybe the merging, I don't know how veritesting helps with this, really. I don't know enough about what veritesting is or why it works. Okay, this is just the stack check thing. I don't know why it is also checked up here. But that's fine. I guess it yeah, because the low byte is gonna be 0. So if it got overwritten somehow, then but we're gonna scan 32 in, so unclear why, because this is a 21 character buffer. I don't know why they have that additional check around the stack cookie, or canary or whatever. Okay, so I still feel like I don't know more about veritesting, but I guess you can just turn it on and let it do its thing. I'm going to skip static binary because it's not super interesting. I mean, it'll be useful to do it, but I feel like I understand what the technique is. Shared library has the function validate, which takes a string and returns either true or false. Oh, I need to probably... Is there lib14? Okay. We call the function from the library. If it returns true, the program prints good job. Otherwise, it prints try again. Note, when you run this script, make sure you run it on the shared object, not the executable. Okay, interesting. This level is intended to teach how to analyze binary formats that are not typical executables. I see. Okay. So still going to do argv1. We can just pass in the name of the binary or the shared object. It's compiled with PIC. You will need to specify the base address. All addresses in the shared library will be base plus offset, where offset is their address in the file. Okay. We'll do 400,000. And set up any symbolic values. You'll need at least one to pass to validate the function, to the validate function rather. Begin the state at the beginning of the validate function as if it was calculated by the program. All right, so let's look at it. syn.validate. It calls entry 0. Interesting. So argc is EBP plus C and our gate. So we've got two parameters. Let's real quick look at the function that calls it. So we push this buffer that we read in and then a length of 8. Okay. Then we are going to come down here and do all of this work. So the validate function address is going to be, let's do this at like 600,000. I don't know that it matters too much, but if the actual binary goes at 400,000 or something, then that'll be problematic. Then we want input buffer is clarify dot bvs, and it's 8 bytes, so 64 bits. And I think we can, and then we'll just say like input len is clarify.bvv, which is 8, and that's 32 bits. I guess the parameter is technically do we have so like we need a 32-bit value that'll actually be the pointer to our input buffer, and that's what we can pass in. But I don't care about getting the let's see if I can do base plus just 1,000. I don't know. That's probably going to be in the middle of the code. So this will be an address. Okay, so these will be our parameters. Begin the state at the beginning of the validate function as if it was called by the program. Determine the parameters needed to call validate and replace parameters with bit vectors holding the values you wish to pass. Recall that clarify BVV constructs a bit vector initialized to a single value. Remember to add the base value specified at the beginning to the function address. Yeah. So the thing is, I also need to set up a like 64-bit input buffer, and then down here you need to add code to inject a symbolic value into the program at the end of the function that constrains EAX to equal true. Just before the function returns. Okay, but I also need to maybe say like initial state dot memory dot store input buffer adder input buffer. Constrains EAX to equal true just before the function returns. There are multiple ways to do this. Search for the address just before the function returns and then constrain EAX. This may require putting code elsewhere. Okay. Right, I think I want the success address to be the end of this. I think that's what they want success address to be about. So here we need to say solution state dot solver dot constraints dot add. No, 8 was constraints. Yeah. Solution state.add constraints. Okay. Then it was just that. Okay. We need to add how do we set up AL is going to be okay. Then yeah, it looks like all right. Set solution state.regs.eax is equal to single one in a 32-bit value, bit vector. So then the solution is going to be solution state.solver.eval input buffer cast to bytes decode. Just really on a lot of these feeling like not very confident. No, I don't want to run it on that. I want to run it on lib. Okay, found something, but of course it has done that before. What? angr shared library.so LD path, is that a thing? LD library path. Does that work? Okay. Hey, somehow what I thought it was doing was correct. So we create some memory space. We have to store it later after we've actually got the state. All of this stuff. Well, this stuff has to come first because these are the parameters. So I just have to like make up a memory address that I will use the pointer to, and then after we have started the state, it hasn't actually simulated anything yet, so we can go ahead and store our bit vector symbol at that address. Then we will run the simulation until we get to the last ending block, at which point we add the constraint that EAX has to be 1 by this point, and then we can solve for what the input buffer needed to have been to get that constraint to pass, basically. Okay. 15. Whew, this is a long one. Okay. It's got all of the source code in here. This binary takes both an integer and a string as a parameter. A certain integer input causes the program to reach a buffer overflow with which we can read a string from an arbitrary memory location. Okay, our goal is to use angr to search the program for this buffer overflow and then automatically generate an exploit to read the string. Good job. Well, that's neat. What is the point of reading the string good job? This CTF attempts to replicate a simplified version of a possible vulnerability where a user can exploit the program to print a secret, such as a password or a private key. In order to keep consistency with the other challenges and to simplify the challenge, the goal of this program would be to print good job instead. Sure. The general strategy for crafting this script will be to search for calls of the puts function, which will eventually be exploited to print out good job. Determine if the first parameter of puts, the pointer to the string to be printed, can be controlled by the user to be set to the location of the good job string. Okay. Solve for the input that prints good job. Structure to implement number 2 before number 1. Okay. So I guess we can look at the code. We've got a 16-byte buffer and then a pointer to a string that we will print. And we read into the buffer first a key, which goes up here, which I think is fine. So first it'll read in 4 bytes. Well, it'll read in a number that it stores in those 4 bytes. And then it will read in 20 characters, which is just enough to fill the entirety of this structure. So we're overflowing the buffer by 4 bytes and getting control of the to print value. And then so depending on what integer we print, it might call puts to print. Nice. Okay. So our goal is to trick this call to puts to print the secret password, which is good job. Okay. I mean, this definitely is more of an interesting challenge. And an example of what I was really curious about is how to use angr to actually do exploit kind of stuff. So we're going to do our own replacement of scanf, it looks like. We'll do entry state. And then we've got the format string. And the 2 addresses. And we will make buffer. We'll make like symbols to store those values. That's what I want to call them, underscore res, just because that's my style. This is going to be 32 bits. And this is going to be 16 bytes is 128 plus another 32 is going to be 160. Is that right? I think so. Yeah. Right, because it's 20 times. Yeah. Okay. Bit vector chop bits equals n function splits the bit vector into a Python list containing the bit vector in segments of n bits each rather. In this case, we're splitting them into segments of 8 bits. Okay. So we're getting the characters from that second one. Ensure that each character in the string is printable. An interesting experiment, once you have a working solution, would be to run the code without constraining the characters to the capital letters. Even though the solution will technically work without this, it's more difficult to enter in a solution that contains characters you can't copy paste or type into your terminal or the web form that checks your solution. If you're using a web form to submit answers, your solution must be entirely alphanumeric except for spaces. Okay. Maybe they're talking about this within the context of like taking this as a class or something where you put in your answers to get a grade. How do you do it in Python? We say ord A. Yeah. Then NDNS only applies to integers. If you store a string in memory and treat it as a little endian integer, it will be backwards. Sure, makes sense. Scanf0 address is going to be do it this way. Okay, and then store those as an array, or Python list, I guess. Then we need to find the symbol. Which is right here. So we'll replace that. And does this make sense? I think so. All right, we will call this whenever puts is called. The goal of this function is to determine if the pointer passed to puts is controllable by the user, such that we can rewrite it to point to the string good job. Okay, recall that puts takes one parameter, pointer to the string it will print. If we load that pointer from memory, we can analyze it to determine if it can be controlled by the user input in order to point it to the location of the good job string. Yes. Treat the implementation of this function as if puts was just called. The stack, registers, memory, etc. should be set up as if the x86 call instruction was just invoked, but of course the function hasn't copied the buffers yet. Stack will look as follows. Yeah, we'll have the return address in first 4 bytes, and then the parameter will be right after that. Okay, puts parameter is going to be, I think load is address and then length in bytes. So this is going to be 20 bytes. No, it's going to be 4 bytes because it's just the pointer. And then it's going to be state.regs.esp plus 4. The following function takes a bit vector as a parameter and checks if it can take on more than one value. While this does not necessarily tell us we have found an exploitable state, it is a strong indication that the bit vector we checked may be controllable by the user. then I assume so we just want to know if the parameter is symbolic rather than look at the memory that it references and then okay. Right, because we we want to check if we can control the pointer itself. Determine the location of the good job string. We want to print it out, and we will do so by attempting to constrain the puts parameter to equal it. Hint, look at RO data. Okay, so we want to do just get the strings. Good job is at this address. Create an expression that will test if puts parameter equals good job string address. If we add this as a constraint to our solver, it will try and find an input that makes this expression true. Take a look at level 8 to remind yourself of the syntax of this. So we need to say puts parameter is equal to good string address, I think. Have angr evaluate the state to determine if all the constraints can be met, including the one we specified above. If it can be specified, we have found our exploit. When doing this, however, we do not want to edit our state in case we have not yet found what we are looking for. To test if our expression is satisfiable without editing the original, we need to clone the state. Okay, so we make a copy, and then we add the constraint to that. Need to add our vulnerable expression as a state to test it. Look at the level 08 and compare this call to how it is called there. Sure. Finally, we test if we can satisfy the constraints of the state. Before we return, let's add the constraint to the solver for real. Okay. So if it's satisfiable, then we'll use that and we'll return true. Else puts parameter, nice extra nice comment. So if it wasn't symbolic, then we didn't call it on user input. Okay, so then in order to determine if we found a vulnerable call to puts, we need to run the function check puts to find above whenever we reach a puts call. To do this, we will look for the place where the instruction pointer state.adder is equal to the beginning of the puts function. So we want puts to be here, I think. Yeah, why not? Right, because I mean, doing it at the jump for the import is fine, I'd say. All right, so successful. It's going to check if we're at that address, and then if we are, it'll be successful if the check for check puts has worked. So then POSIX.dumps scanf is not I guess what we can look for is, why don't we try it that way? But we could also attempt to dump. God damn it. Dump those scanf variables, yeah. Join solution state.solver.eval. No. Ugh. So do this. All right, so maybe that's good enough to get it to print. Good job. Yeah, I guess the address happens to, it's weird. Happens to be at what do we want? G J O H, yes. Wait a second. Yeah. GHJO. Okay. Cool. They happen to put it at a spot that has all uppercase so that we can easily print it. But yeah, I see what they were talking about with those constraints. Whereas, you know, it doesn't have to be at an address that winds up that nicely. Cool. That is, you know, I feel like I should try to go back to a bunch of like simple buffer overflow things and make use of angr in trying to tackle them, because being able to solver. So I don't know. Like, at least in this very simple example, the majority of what I would find beneficial is just determining that we can control that value. I don't need a constraint solver to I probably don't need a constraint solver to figure out if I can input a value that then is the address of the thing I want to print if I'm just overflowing into an address field. But I guess the constraint solver would come in handy if there was some manipulation of that value. So I had to provide it in like effectively in an encoded way, and the result of the decoding would end up being a certain address value that I wanted to control. Then I could use the constraint solver to work backwards to figure out what the input needed to be. But in this case, the input is exactly, other than the fact that we've got the other parts of the input, the bit that is the that is the actual overflow to define the pointer is it's equal to the pointer itself. Okay, then what do we want to do? We'll do the next one. This one is arbitrary right, so also taking advantage of some exploitability. The program does the following. It reads a signed integer into key, and then 20 bytes of string data into user input. Certain unknown conditions are true. Oh, that was the other thing that we needed for angr, is like getting that first parameter, I guess. So sort of combining angr and more traditional exploit analysis stuff in the last one. And I assume same here, because we have unknown conditions that result in str and copy from user input into a random buffer. I don't know what random buffer is about, but I'm guessing it's not really random, and maybe we have a way of controlling what random buffer is. And then okay, and we can control it so that secure buffer is equal to, like, what we're writing user input into is the secure buffer rather than the original random buffer value, and we use input, what we have as user input is the same as the reference string, is my guess. Okay, if this program has no bugs in it, it should always print try again, since user input copies into random buffer, not secure buffer. The question is, can we find a buffer overflow that will allow us to overwrite the random buffer pointer to point to secure buffer? Yes, we can, but we will need to use angr. We want to identify a place in the binary when strncopy is called, when we can control the source contents, not the source pointer. This will allow us to write arbitrary data to the destination. Okay, I'm going to reread that, but first, it has occurred to me that I haven't popped into OBS in a minute or two, by which I mean like since the beginning of the stream, so most likely OBS is going to crash when I pop over to it, and just want to give you all a heads up before I do that. The stream is going to die in all likelihood in a minute or so. Well, a lot less than a minute. Okay, and we're back. So let's read that bit again. We want to identify a place in the binary when strncopy is called, when we can, 1, control the source contents, not the pointer, okay, and the destination point. I see. So we want to control what's inside of user input and the value of the random buffer variable. So whatever user input points to, we want to be able to control, and whatever random buffer is, most likely a stack variable, we want to control that as well. This will allow us to write to an arbitrary location. Yeah. If we can meet both of these requirements, we can write arbitrary data to an arbitrary location. Finally, we need to constrain the source contents to be equal to the reference string and the destination pointer to be equal to the secure buffer. Okay. See, I feel like if we can do this, right, then, you know, we also bring in pwn tools, and we could write to the global offset table and stuff, or, you know, there's a lot you can do with an arbitrary data write to an arbitrary location. Okay, so let's start with project.factory.entry state, and we're going to replace scanf with our 2 variables. First one is 32 bits, second one is 160 bits. Okay, and then we're going to chop it, and I guess the address we want to write to is also going to be happens to be all uppercase letters. Then scanf address, it's just going to be scanf header, and do that for the scanf1. The usual thing. Need to check out the binary itself. Okay, then scanf address is here. So again, we can hook scanf and keep track of what gets written to by it, and have access to those bit vector symbols that we created. In this challenge, we want to check strncopy to determine if we can control both the source and the destination. It's common that we will be able to control at least one of the parameters, such as when the program copies a string that it receives via standard in. Okay, so the source is going to be state.regs.esp plus 4, 8. Oh yeah, okay. So it's at 8. The destination regs.esp plus 4. Oops. And then this is at C. Let's just do it that way. Then the contents we want to load from the source, we know it's going to be 20 bytes. And we want to figure out if source contents is symbolic and states.solver.symbolic stern copy dest. So yeah, if the destination parameter is symbolic and the contents of the source parameter are symbolic, use ltrace to determine the reference string. Decompile the binary to determine the address of the buffer it checks the password against. Our goal is to overwrite that buffer to store the password. Interesting. So it's not necessarily this one. Maybe it generates the the reference string. Password buffer. So we copy password into password buffer, and then we compare it against this string. So I guess we don't need to use ltrace. And the address of the buffer it checks the password against. So that's going to be password buffer, which is just, oops, where did I go? Let's just double check. Yep. Also a printable address, 57, 58, 43, 44. Okay. Create an expression that tests if the first n bytes is length. Warning. While typical Python slices will work with bit vectors, they are indexed in an odd way. The ranges must start with a high value and end with a low value. Additionally, the bits are indexed from right to left. Sure, that makes sense. For example, let a bit vector b equal ABCDEFG. The following will read bits 0 through 7. Total of 1 byte from the rightmost bit. Yeah. Because, I mean, it's basically big endian. And we give high values, the big end values first. So, but what is the thing? The test if the first n bytes is length. Okay. I mean, we just want to check if the contents, we want to constrain the contents to be equal to password string. So we want bits, how long is the password? 1, 2, 3, 4, 5, 6, 7, 8. So bits 64 through 0, 63 rather, through 0. Although we need it to be the first bytes, so it's actually 159 through what? What is this? Jesus Christ. I don't know what the hell I ended up doing there. I meant to hit a question mark first. Yeah, I don't know what the fuck I got into there. Oh, why did I reopen? Whatever. 60 minus 64 is going to be 96. So if those first 8 bytes, I guess. Oh. So I can just use negative values. -1 through -64 should be the first 8 bytes. Okay. Seems fine. We can use our math skills. To calculate some stuff for us. Does dest equal buff address? So we gotta say strn copy dest is equal to buffer address. And then we will add those constraints. Yeah, so I see we copied the state and added it and then determined if the constraints of the new state were satisfiable. Since the pattern is so simple, or so common rather, angr implemented a parameter extra constraint. So we can check if it's satisfiable with some additional constraints that don't store them yet. And if that's true, then we add those constraints and return true. Sounds good to me. So successful is, let's get the stern copy. Address in there. And we need do I have that? Yes. Okay. We actually want scanf 0 res, scanf 1 res, and then scanf 0 solution is okay. This feels decently like it makes sense based on how the last one worked. Couldn't find the solution though. Filling memory with 236 unconstrained referenced from string copy 0. What have I done wrong here? So let's see, when we get, so we search around until we get to the call that takes us to the string copy import, and or just in general, if we're there, then we will call check with the state, and we're going to get our parameters. So I think the way that we're doing this is wrong, because this is going to be this is going to be the address on the stack. So we need to dereference it. Make a concrete source version of the source pointer. And that'll be 20 bytes. And just 4 bytes there. And then again, dest pointer. String copy dest 4. Get up there. So maybe this will work. Concretize. How do you make it concrete? Under program state. guess we'll just eval it. I mean, can I load? Probably not. Source pointer. Hey, does that work then? No. It's definitely controlling it. So this should WXCD, I'm guessing, is overriding the destination pointer to then be the address of which string? Well, first off, yeah, it's not constraining it. Maybe we shouldn't eval it, but I feel like the source pointer should be, we're not overriding that with user input. So maybe it's not 20. I guess let's look at the main function. It's only doing 12 bytes. Or 16 in some of these other strn copies. I see. And the scanf results will still be 20 bytes though. But it's still not constraining that input. Does source hold password? Should be the contents are, I mean, if we know it's 16 bytes, right, then 128 bits minus 64, so 127 to 64. Still no. Unless I'm getting the wrong bits. We're only calling scanf once, I think, so yeah, it's gonna be, I've pushed the pointer on, so ESP plus 4, or rather plus 8 is the address at the beginning of the buffer. So can we do just gonna print out yeah, they are BV32 values. So we could try that. Interesting. But again, doesn't. It's the same length. Yeah. Like, I think it's still gonna segfault. Yeah. Where did it even segfault? Somewhere in libc. From strn copy. But we only want to, no, because we're going to copy 16 bytes. Oh, well, we should definitely, oh, it might be from some of these other ones. we need to concrete size outside allowable limits. What the heck? Can I do it without evaluating? So what do we do for this one? We loaded from that address 4 bytes. Okay. Oh, this is probably, I see. Then okay. Yeah, now it works. So we were not loading those pointers in the correct endianness. Good job. Way to go. Alright, and that makes sense. This was backwards. Well, we have hit the limit of my time, I think. We've got one more. Oops. And I'll tackle this at the beginning of the next stream where I do angr related stuff. And we'll see, you know, how this relates, but then we're just gonna move on to, yeah, this is all of them. Gonna move on to, oh, well, I guess this one's not done yet, so I'm not gonna worry about that. We're just gonna move on to trying out high school CTF 2019 A byte, and see if we can use angr for that. And that will be on Wednesday. Tomorrow we are going back to continuing to work on the x86 instruction decoder. So that's Tuesdays and Thursdays. And then Monday, Wednesday, Friday, we're going to do hacking challenges. We'll do the angr stuff. And at some point, we'll be done with that and we will move on to ROP stuff, which, I mean, we've done that before, but this is, I guess, more hardcore ROP stuff, I suppose. And eventually we will get into heap exploitation. Real quick, I want to give a mention to a resource that I'm going to use before we get to the heap exploitation. Somebody linked this on Twitter and it sounded really good. This Linux heap exploitation on Udemy. The price here is in Thai baht, but it's like $20 basically. And this seems like it's perfect for what the practice I want to do before I start trying all of those heap exploit challenges in the Nightmare course. Apparently it is by Max Camper, who created ROP Emporium, so definitely somebody who knows their stuff and is, has a history of trying to like teach and provide resources for other people, and clearly in the vein of like, challenges to work on so that you're actually practicing. You're not just reading an info dump of the concepts, because you really need to practice it before you can be confident that you're able to apply those skills. And yeah, so that all seems great. And something I was looking up, and I'm gonna go ahead and throw this in chat, and I'll link it again when we get around to that. Who knows? That'll probably be a couple weeks at least. But someone mentioned. Oh no, that's what I was doing. I was looking around, and it looks like this is one of the trainings that he has given at various like conferences, or at least one conference that I saw. And the price of $20, obviously it does not include the like one-on-one interaction with the teacher. I'm assuming at this kind of price it doesn't make a lot of sense. It's more just self directed kind of learning stuff. But if it's the same material that you would get in one of these, $2,000 trainings, then I'm more than happy to have access to it for $20. I think it's incredibly generous of Mr. Camper to offer that. So I just wanted to make everybody aware, if you're watching this, if you're watching the VOD or something and you're interested in learning about heap exploitation, and read through the info, make sure that you actually are at a place in your journey to exploiting stuff where this information is going to be useful. Like if you are not very familiar with assembly code, it's probably going to be kind of difficult, it would be my guess. Just like this is not the simplest kind of exploitation you can do, but make a assessment for yourself, and if it seems right, I'd say check out the preview and go ahead and pick up the course. I'm definitely going to do it because I think this will be a great way for me to learn how to do that kind of exploitation. And if I need more resources afterwards, I have a couple others that I'm looking at, but this seems like my number one go-to for sure. So again, thank you to everybody that's watched the stream, everybody that was talking in chat, and if you're watching this on the VOD, thanks as well. And I'll be back tomorrow.